So far we looked at calculation of fugacity and fugacity coefficient using virial equation of state. We have also used Lee-Kessler tables to calculate these quantities, but they have a limited range of pressures over which they can be applied, as you know. How do we calculate fugacity and fugacity coefficient at other conditions? How do we do that for liquids? To answer that question, we can go back and revisit our discussion on cubic equation of state. And if you recall, for a variety of cubic equations, we have a general expression that we have used. Right. The general cubic equation of state is given by the expression I have in here. P is RT by V minus B minus A by a quadratic in V. The parameters for the equation of state A in some cases will depend on temperature. In some cases they may not, as in case of van der Waals equation or Redlich-Kwong equation. They will not depend on temperature, but in general it is a function of temperature. B is only dependent on the critical properties, and from that we calculate a host of parameters based on these two parameters A and B, and we can use cubic equation of state, as we have seen in our earlier discussion, to calculate the molar volume or the compressibility factor Z. We have also used it to calculate the residual properties such as residual enthalpy, residual entropy, and residual Gibbs free energy. We have developed expressions for those. What we will do is use those expressions and also try to calculate fugacity and fugacity coefficient. If you recall, we said that the fugacity coefficient ln phi for pure species is gr by RT, and this equals, for a cubic equation of state, Z minus 1 minus ln of Z minus beta minus Q times I. And Z is the compressibility factor at the condition we are looking at. Beta, Q, and I are given in the expressions here, beta, Q, and I, depending on whether we have the same value for epsilon and sigma or different values for them. So once I know a cubic equation of state, and given a temperature and pressure, I can calculate the compressibility factor and all the other parameters that are listed in here, and use those to calculate the fugacity or the fugacity coefficient. Let us try to demonstrate this calculation using an example. But before we do that, I should emphasize that this is a cubic equation of state, which means at certain conditions it may have three real roots corresponding to the vapor-like root, the liquid-like root, and the metastable state. And in that case, we have three values for compressibility factor Z. So which one do I use for calculating the fugacity coefficient? The answer lies in the fact that what fugacity coefficient am I trying to calculate? If I am trying to calculate fugacity coefficient for the liquid, then I will use the liquid-like root. If I am trying to calculate fugacity coefficient for the vapor, then I will use the vapor-like root. Having said that, let's try to demonstrate this calculation in one example. So in this problem, we are interested in calculating fugacity and fugacity coefficient for ethylene at 373 Kelvin and 30 bar using van der Waals equation of state. To be able to use the equation of state, the first thing we need are the critical conditions, critical constants Tc and Pc. For ethylene, if you recall, Tc was 282.3 Kelvin, Pc was 50.4 bar, and omega is 0.087. At the given conditions, I can use the equation of state parameters listed in here and calculate beta and Q. Turns out for this condition, beta is going to be omega PR over TR, and this value turns out to be 0.056312. Q is psi alpha by omega TR, and for this particular case the value turns out to be 2.5543. Remember, alpha for van der Waals equation of state is 1. Now once I have beta and Q, the next thing we want to do is calculate the compressibility factor at the given conditions. And to calculate the compressibility factor, if you recall, what we did was to solve the cubic in Z, right? And the cubic in Z had this form. This is a lengthy expression. We can actually get rid of epsilons and betas, epsilons and sigmas for van der Waals equation of state, and the equation actually looks much simpler than this once we do that. But I'm writing it for sake of generality. Once we do that, this is the cubic in Z we want to solve. We can simplify this and substitute the values of beta, Q, epsilon, and sigma. For van der Waals equation of state, both epsilon and sigmas are 0 if you recall from the table. And once we do that, we get the coefficients for this cube polynomial, and it turns out to be Z cube plus, rather in this case, minus 1.0563 Z square plus 0.1438 Z minus 8.09910 power negative 3. This equals 0. This is the cubic in Z we get for the equation of state. We can solve this cubic to obtain the 3 roots, and in this particular case it turns out that only one root is real, and that real root of course corresponds to the vapor-like volume because it's much closer to 1, and that value turns out to be 0.90774 Z, the compressibility factor. Once I have that value, I can go back and calculate GR by RT or ln phi, which is Z minus 1 minus ln Z minus beta minus Q times I. So I have beta, I have Q, I have Z. What I don't have is I. And for van der Waals equation of state, epsilon is sigma. So I is beta by Z plus epsilon beta, right, which is essentially beta by Z, since epsilon equals sigma equals 0 for van der Waals equation of state. So this value, once I have Z, I can calculate this value, and this value turns out to be 0.06204. That's the value of I. Once I have I can put everything back in this expression for ln phi. So it will be 0.9077 minus 1 minus ln of 0.9077 minus 0.056312 minus 2.5543 times 0.06204, and this equals ln phi, which is negative 0.0899. This is the value of ln phi we will get by simplifying the numericals, and once we have ln phi, I can calculate phi. It will be exponential of negative 0.0899. That's the value of ln phi. This is 0.914. And once I have phi, I can calculate the fugacity f. It will be 0.914 times 30 bar, which is 27.42 bar. So I can use a cubic equation of state and calculate fugacity. We almost follow exact same procedure as we did for calculation of the residual properties, in particular residual Gibbs free energy, and then from there we can calculate the fugacity. So that demonstrates the use of cubic equation of state for calculation of fugacities. Now what we have done so far is looked at using a variety of PVT equations to calculate the fugacity and fugacity coefficient of pure species. In fact, the last approach we have used for cubic equation of state can also calculate the fugacity of pure liquid if I use the liquid-like volume or liquid-like compressibility factor from the cubic equation of state solution, if that exists at the given condition, of course. Next, what we will try to do is try to extend our discussion to fugacity of species in the mixture. For an ideal gas mixture, of course, recall that Fi hat will be equal to the partial pressure, so it will be Yi times P, because phi hat for an ideal gas mixture needs to be equal to 1. Next easiest equation of state we can use is a virial equation of state. The first thing we need to answer is how we can write virial equation of state for a mixture. Virial equation of state using only the second virial coefficient is written as Z is 1 plus Bp over Rt. This was for a pure species. I can write an analogous equation for a mixture. The compressibility factor for the mixture is going to be B for the mixture, P over Rt. Recall that the second virial coefficient in case of a pure species is only a function of temperature. B pure is only a function of temperature. In case of a mixture, obviously, it will be a function of temperature as well as the mole fraction, because it's gas, let's call it as Y. So it will be a function of both the temperature and mole fraction. One can actually derive an expression for B mixture from statistical mechanics, and it turns out that B for the mixture is given by this expression here. In a multi-component mixture, it is sigma over I, sigma over j, yi, yj, bij. Now, if I expand this summations for a binary mixture, it turns out to be B mix is y1 squared B11 plus 2y1 y2 B12 plus y2 squared B22. Now, if you notice, the expression for B mixture contains 3 virial coefficients in addition to the mole fractions. Let's rewrite that equation again. B mix is y1 squared B11 plus 2y1 y2 B12 plus y2 squared B22. This is a binary mixture. In a binary mixture, obviously y1 plus y2 is 1, and given a mole fraction we can calculate the other one. The other thing that appears in this expression is virial coefficients, 3 of them, B11, B22 and B12. B11 and B22 are the pure virial, or the virial coefficients for the pure species 1 and 2 respectively. B12 is what is called as a cross coefficient for a mixture of 1 and 2. We'll come back and see how one can calculate B12, but for now it suffices to say it is also a virial coefficient that depends only on temperature. The composition dependency for the mixture is given by the expression we have on the top. We call this as a mixing rule. Because we are writing a property for a mixture, we call this as a mixing rule. This is how we mix the virial coefficients to obtain virial coefficient for the mixture. This mixing rule contains 3 virial coefficients, B11 for pure 1, B22 for pure 2 and B12 which is the cross virial coefficient. All the 3 of them are functions only of temperature. When we try to solve a problem, we'll come back and talk about how one can get B12, but for now we will carry this discussion forward and see how we can actually calculate fugacity coefficient and fugacity of species in a mixture given these 3 virial coefficients B11, B22 and B12. To do that, what we have to do is go back to the definition of fugacity coefficient. Remember that ln Vi hat is Gi bar R over RT. So this is the derivative of NGR by RT with respect to Ni at Pt and Nj, right. Now, NGR by RT by itself is N times GR by RT, if you recall, is integral 0 to P Z minus 1 dP by P. So derivative of this with respect to Ni is what we are interested in. Let's take N inside. It will be Nz minus N dP by P. So Gi bar R by RT then will be derivative of this with respect to Ni. So we can take the derivative into the integral. It will be derivative with respect to Ni of Nz minus N at Pt and Nj dP over P. And that will be integral 0 to P, derivative of Nz over Ni, we can call it as partial molar compressibility factor for Zi bar minus derivative of N with respect to Ni, if you recall, is 1 dP. Now, what I'm interested in is then finding Zi bar, or the derivative of Nz with respect to Ni. Derivative of Nz with respect to Ni at Pt and Nj. To do that, let's use an equation of state. In this case, we are interested in using virial equation of state. If you recall, for virial equation of state, Z mix is 1 plus B mix over RT times P, right? And N times Z, I'm just omitting the subscript, mixture, of course we're talking about a mixture, is simply N plus N times B P over RT. And the derivative of this quantity with respect to Ni at Pt and Nj is going to be 1 plus the temperature and pressure are constant, so I can take those out of the derivative, which means I can get P by RT out of that derivative. So what I will have left is P over RT derivative of NB with respect to Ni at Pt and Nj. Recall that B for the mixture is a function of Yi, so Nb will be a function of Ni. So that's why I did not take B out of that derivative. Although the temperature is constant, for a mixture, B itself is going to be a function of the mole fraction, or Nb will be a function of Ni. So then what I'm looking at is trying to obtain a derivative of Nb with respect to Ni and Pt at Pt and Nj. Once I do that, I can easily get the fugacity coefficient for species I. So what we'll do is consider a binary mixture to demonstrate how we do this, and then we can generalize the result we obtain. For a binary mixture, we said B is y1 squared B11 plus 2y1 y2 B12 plus y2 squared B22. N times B is going to be N1 squared over N times B11 plus 2N1 N2. When we take the derivative with respect to Ni, right, remember that we want to convert all the mole fractions into number of moles, N1s, N2s and Ns, right. We cannot leave mole fractions in there because we are taking derivative with respect to N1 or N2. So what I did is converted y1 squared by N squared and multiplied it with N, so that what I will have left is N1 squared over N B11 plus 2N1 N2 over N B12 plus N2 squared over N B22. So now I have converted everything in terms of moles. There is no mole fraction left on the right hand side. Now I need to take a derivative with respect to, let us say, n1. Then derivative of nb with respect to n1, because there are only two components, what I am holding constant is n2, t and p of course. This value will be, I am holding n2 constant, so this value will be b11 times 2n n1 minus derivative of n with respect to n1 is 1, so it is n1 squared over n squared, plus 2 times n2 is constant, b12 is constant. What I have left inside to take the derivative is n1 over n. Derivative of n1 over n with respect to n1 will be n minus n1 over n square. Plus finally, what I have is b22 n2 squared, and derivative of 1 over n with respect to n1 will be negative 1 over n squared. I can simplify this, and if you see, I can rewrite all the n's and n1's in terms of the mole fraction y1 back. So what I get finally is going to be 2y1 minus y1 squared b11 minus y2 squared b22 plus 2y2 squared b12. Notice that this will be 1 minus y1, which is y2. This y2 multiplied with, this will be 1 minus y1 by n. So I can obtain the derivative of nb with respect to n1. This can be further simplified to put it in a general form. It turns out that this value of derivative of nb with respect to n1 at pt and n2 can be written as b11 plus y2 square delta 12. This delta 12 is given by 2b12 minus b11 minus b. We can further simplify that, right? And once we have this value, I can easily write ln phi 1 hat. This is p over rt times derivative of nb with respect to n1, which is b11 plus y2 square delta 12. And ln phi 2 hat is going to be p over rt b22 y1 square delta 12. In general, for a multi-component mixture, ln phi k hat is written as p over rt bkk plus half double sigma I j yi yj 2 delta ik minus delta ij. This is a general expression for a multi-component mixture, but for our discussion here, it suffices to say that these expressions for binary mixtures should be sufficient. So what we have done essentially is derived an expression for fugacity coefficient in a binary mixture in terms of the virial coefficients b11, b22 and delta 12, which includes the cross virial coefficient b12 in addition to temperature and pressure. So given the virial coefficients, we can readily obtain the fugacity coefficient of the species. So this expression here gives us the fugacity coefficient of species in a binary mixture or in general a multi-component mixture, relating it to the pure component virial coefficients and the cross virial coefficient bij. One question still remains unanswered: how do we obtain the cross virial coefficient bij or b12? One can obtain them from experiments if we study the behavior of the mixture. If not, we resort to empirical means to obtain this cross virial coefficient b12. One of the ways that is proposed is to use what are known as pseudo critical constants. To obtain pseudocritical constants, we use a set of what are known as combining rules. Differentiate them from the mixing rules we have used to obtain the properties of a mixture, for example, B mix. And in combining rules, what we do is use empirical formulae to calculate these pseudocritical constants. So these combining rules give us pseudocritical constants, and by pseudocritical constants what we mean is that we obtain the constant Tc12 using the pure component Tc1 and Tc2 via this formula. Similarly, we take the arithmetic mean for obtaining the compressibility factor at the critical condition ZC12 and the eccentric factor omega 12. Both of them are given by their respective arithmetic means, and the volume Vc12 is given as arithmetic mean of their cube roots. Essentially, we are taking some sort of a arithmetic mean of the size of the particular molecule we are considering. And finally, Pc12 is, since PV is ZRT, Pc12 will be given by this equation here. So these are the empirical combining rules we use if we don't have any experimental data to calculate B12. Once we define the pseudocritical parameters using these combining rules, what we can do is obtain TR12 and PR12. Now I have TC12 and PC12, so TR12 is going to be T over TC12. This will be P over PC12. So once I have this combining rules, I can use it to calculate the reduced temperature TR12 given as T over TC12. Once I have TR12, I can use this reduced temperature TR12 to calculate B12 or the cross-virial coefficient. The way we do that is use the theorem of corresponding states, and in one of the previous problems we calculated B0 via this correlation and B1 using this correlation, right? And we combined B0 and B1 to obtain the virial coefficient B. We did this for a pure species, right? And we said B is RTC by PC B0 plus omega B1. What we will do is we will use the same correlations, but this time to obtain the cross-virial coefficient B12. The way we do that is we'll write a general expression for Ij, right, in an analogous equation, and so let's simply use that subscript here. To get Ij, what we will do is use the reduced temperature Trij in these two equations, and what we get is B0 Ij and B1 Ij, and we use those B0 Ijs and B1 Ijs along with TCij and PCij to obtain Bij. And the values of I and j in a binary mixture can be 1, 2, j also can be 1, 2. So I can use these equations to obtain all the three virial coefficients. B11, if I equal to j equals 1, then what I get is B11. If I equals j equals 2, what I get is B22. If I is 1 and j is 2, what I get is B12. Of course, in this formulation, the idea is that B12 is going to be equal to B21. So whether I is 2 and j is 1 or j is 2 and I is 1, we obtain the same values. So B12 is essentially B21. Both of them are identical. So this is how we will obtain our cross-virial coefficient. Let's demonstrate this using an example. We want to find the fugacity coefficient and fugacity for each species in a binary mixture of ethylene and propylene at 373 Kelvin and 30 bar. We should of course have been given a value for the composition of this mixture. Without that we cannot obtain the fugacity coefficient, right? So let's say Y1 is 0.4 in this particular problem, and 1 stands for ethylene, 2 stands for propylene. So then let's restate the problem. We want to obtain the fugacity and fugacity coefficient for each species in a binary mixture of ethylene and propylene, ethylene being 1 and propylene is 2. The mole fraction of ethylene in this mixture Y1 is 0.1. We want to use virial equation of state to do this particular calculation. So we're going to use the formula we wrote earlier. B naught, we want to obtain it using this equation. B1 using this equation. These are the two virial coefficients related to the temperature or reduced temperature, and B of course is RTC by PC, B naught plus omega B1. We can use it to obtain all the three virial coefficients 1, 1, 1, 2 and 2, 2, right. So if you recall, we said that the fugacity coefficient ln phi1 hat is P over RT B11 plus Y2 square delta 1, 2, and ln phi2 hat in the binary mixture is P over RT B22 plus Y1 square delta 1, 2, and delta 1, 2 was 2B12 minus B11 minus B22. So to obtain the fugacity coefficients phi1 hat and phi2 hat for ethylene and propylene, I need the temperature and pressure which are given to me, the composition Y1 and Y2 which is also known. So all I don't know to use those equations are the virial coefficients B11, B22 and delta 1, 2 which of course needs B12. So once I have these three virial coefficients, I can come back and use these three virial coefficients along with the other information in these two equations to get the fugacity coefficients of the two species. So then my first task is to obtain the three virial coefficients, and we're going to use the equations listed above to obtain B naught B1 and hence Bij. I do that. B naught and B1 for the pure species 1 and 2 are easy to obtain, but for the cross virial coefficient B12 I need the pseudo critical parameters. We will use the combining rules we talked about earlier to get those values. First, let us list ethylene, propylene and the pseudo constant 1, 2. Let's list each of the critical parameters. Tc, let's talk about Tc, Vc, Zc, omega and finally Pc. Tc for ethylene is 282.3 Kelvin. For propylene it is 365.61 Kelvin, and Tc12 321.3. This is square root of Tc1 and Tc2. Vc in cc per mole, maybe I should write the units here. This is cc per mole. These two are dimensionless and this will be in bar. Okay. Vc is 131. For 2 it is 188.4, and using the combining rule we get Vc12 as 158. This was Vc1 to the power 1/3 plus Vc2 to the power 1/3 over 2 whole cube if you recall. Zc and omega are simply arithmetic averages. This is 0.281, this is 0.289, and average of that is Zc12 which is 0.285, and omega, this is 0.087, this is 0.14, and average of that is 0.1135. And finally Pc is 50.4, this is 46.65, and once we have all the other parameters Tc, Vc, Zc, we can calculate Pc as Zc12 R Tc12 by Vc12. And this turns out to be 48.19. This is the value of Pc12. So now once I have the critical parameters for 11, 22 and 12, I can calculate the reduced temperature first. So I'm going to formulate a similar table again for 1, 2. The reduced temperature is going to be T over Tcij, and in this case it will be 1.32. Remember that Tc is 370, T is 373 Kelvin. So T over Tci11 is 1.32. This is 1.02 and this will be 1.16. And using this T, I can calculate B0 and B1. This will be negative 0.1872. This will be negative 0.3257 and this will be negative 0.2493. B1 is 0.0856, negative 0.0191 and 0.0471. Once I have B0 and B1, I can calculate B, which is B0 plus omega B1 times R Tcij by Pcij. I will use that expression to calculate B, and in this case B turns out to be negative 83.72. This is in cc per mole, negative 213.97 and negative 135.23. Once I have B, right, and I have obtained, recall that I have obtained B0 and B1 using the formula we listed here in terms of TR, right, and then B, of course. Once I have B11, which is negative 83.72, B22, which is negative 213.97, and B12, which is negative 135.23, I can calculate delta 12, which is 2, B12 minus B11 minus B22. That will be 2 times negative 135.23 minus 83.72 minus 213.97, and this value turns out to be positive 27.23. Once I have delta 12, I can calculate ln phi1 hat and ln phi2 hat. I'll go back to this equation here to calculate ln phi1 hat and phi2 hat, these two equations. Now I have B11 delta 12 P over RT, right? So ln phi1 hat is going to be P over RT times B11 plus Y2 square delta 12. I'm sorry, Y1 square delta 12, right? No, it's Y2 square delta 12. So once I have all those quantities, I can write ln phi1 hat, right? Ln phi1 hat is going to be P over RT B11 plus Y2 square delta 12. That will be, the pressure here is 30 bar, R is 83.14 in bar cc per mole per Kelvin. This is 373 Kelvin times B11, which is negative 83.72 plus Y2 square, which is 0.6. Y1 is 0.4, so Y2 is 0.6 whole squared. Delta 12 is 27.23. And if I simplify that, what I end up with is negative 0.0715. And similarly, ln phi2 hat is going to be negative 0.2028. Once I have ln phi1 hat and phi2 hat, I can calculate the fugacity coefficients in the mixture. Phi1 hat is going to be exponential of negative 0.0715, which turns out to be 0.93 1 and phi 2 hat is going to be exponential of negative 0.2028, which turns out to be 0.816. And F1 hat by Y1P, this is phi 1 hat, which means F1 hat is going to be 0.931 times Y1, which is 0.4 times 30. So that will be 11.17. And similarly, F2 hat is going to be phi 2 hat, which is 0.816 times Y2, which is 0.6 times P 30, which is 14.7 bar. So we go through the series of steps, first to calculate the cross virial coefficient and the pure component virial coefficients after obtaining the pseudo-critical parameters using the combining rules. And once we do that, rest of it is pretty straightforward to calculate the fugacity coefficient and hence the fugacity of species 1 and 2 in the mixture. Now notice that in this particular mixture, the partial pressure P1 is Y1P, that is about 12 bar, and P2 is Y2P, that is about 18 bar. So as opposed to the partial pressure 12 bar, the fugacity of species 1 is about 11.1 bar because of the non-ideality, and F2 hat as opposed to 18 bar is about 14.7 bar. So that the values of the fugacity coefficients or the fugacities in that sense demonstrate how far away we are from ideal gas behavior. So that completes our discussion on fugacity coefficients of gases using virial equation of state. When we come back in the next video, we're going to try to use a cubic equation of state to calculate the fugacity coefficient of species in the mixture, and following that we will look at other methods to calculate fugacity of liquids. Thank you and see you in the next lecture.